My name is Fahrig, and today I'm giving a 6-minute talk on the detection of gravitational waves. So, some of you might have heard recently they reported on the discovery of gravitational waves at the LIGO facility in Livingston Parish. And as an engineering major, I didn't know much about it, so I felt kind of out of the loop. Probably something I should know about. So I thought I'd learn a bit about it and share my vast knowledge that I acquired with my classmates. So, all right, a little bit of background. The actual detection occurred on September 14, 2015. The gravitational waves were detected by both the LIGO detectors. There's one in Livingston, and then there's one in Hanford, Washington. And the Hanford, Washington location actually got the chirp around, I think it was like 7 milliseconds after what occurred in Livingston. So this confirms a major prediction of Albert Einstein's general theory of relativity. And, so the gravitational wave are ripples in space and time caused by highly energetic and violent events in the universe. The general relativity theory states that black holes orbiting each other lose energy through the emission of gravitational waves, and they gradually start to approach each other over billions of years. And then in the final fractions of a second of their approach, they actually combine, and a portion of the black hole's mass is converted to energy, and that's where the E equals mc squared relation comes from. And then the energy that's emitted is emitted at a strong burst of gravitational waves. So gravitational wave research, well, it was initially proposed by Albert Einstein in 1915, and then the existence was first brought to light through the research of Joseph Taylor Jr. and some of his colleagues. In 1974, a binary system of a pulsar in orbit around a neutron star was discovered by Taylor and Russell Hulse. A pulsar is a pulsating radio star. It emits a beam of electromagnetic radiation. In 1982, Taylor and Joel M. Weisberg discovered that the orbit of the pulsar was shrinking over time due to the release of energy, so it's getting closer to that neutron star. And this proved, and the release of energy was due to gravitational waves. And this proved that the measurement of gravitational waves would be possible. So, this is LIGO, this is the Livingston Parish location, and LIGO stands for Laser Interferometer Gravitational Wave Observatory. It's not a traditional observatory per se. It's not like a big telescope or anything like that. It's actually just an extremely large-scale physics experiment, basically. There's 2 locations. In Livingston and Hanford, Washington, and they were both conceived, built, and operated by Caltech and MIT. So the LIGO facilities are basically modeled after a basic Michelson interferometer, and what happens is a laser is shot to a beam splitter right here, and the beams are split into 2. They go down each arm, and beams are sent to the mirror and then reflected back, and whenever they're reflected back, they're going to combine again, and if both of the arm's lengths or the distance that the beams travel are exactly the same, then the photo detector down here won't sense anything, or that's how LIGO's photo detectors are set up. But if the beams do not travel the exact same length, or the arm length isn't the same, then that means that there will be a change in light intensity, and this change in light intensity means that there was a change in distance of the actual arm length. So, like the arm that's built is actually changing, not the beam. So, at LIGO's facility, they have these, the arms, they're only 4 kilometers, they're only built that way, but they use these cavities to make the distance the beam traveled to about 11, 20 kilometers, so that's a lot more than they'd be able to build traditionally. Then they use power recycling mirrors down here that would be placed in between the laser and the beam splitter in order to recycle the power, because the laser only starts off with about 200 watts of power, but it needs about 750 kilowatts to sharpen the interference pattern and increase the resolution of the And I forgot to mention the increase in the distance helps sharpen the sensitivity of the interferometer, and that makes it to where the interferometer is able to detect a change in arm length of up to as little as thousandths, like one or some fraction of the arm length smaller than the mass of the proton. So pretty small. So the results, they were detected on September 14th. The masses of black holes that were involved in the event were estimated to be about 29 to 36 times the mass of the sun, so pretty big. The event took place 1.3 billion years ago. It's about 3 times the mass of the sun was converted to 2 gravitational waves, and the power output of the event peaked at about 50 times the power of the whole visible universe. This was the first observation of an actual gravitational wave. The contributions to LIGO research is conducted by the LIGO Scientific Collaboration. It's composed of more than 1,000 scientists and 250 students from more than 90 universities in the United States and 14 different countries. So what's next now that we've found these gravitational waves? And I have a couple quotes. This detection is the beginning of a new era. The field of gravitational wave astronomy is now a reality. And that was said by Gabriela Gonzalez, the LSC spokesperson. She's actually a professor of physics and astronomy at LSU. And also, with this discovery, we humans are embarking on a marvelous new quest, the quest to explore the warped side of the universe, objects and phenomena that are made from warped space-time. Colliding black holes and gravitational waves are our first beautiful examples. And that was said by Kip Thorne, Caltech's professor of theoretical physics.